I'm Mathilde Rosi-Marshall from University of Virginia. I'm going to be talking about an evaluation of a matrix-based feedback analysis in a globally resolved energy balance model, and I'll get to explaining what all of that means in just a moment. I'd like to acknowledge my mentor here at OWU, Dr. Craig Jackson, as well as our collaborator, Dr. Vladimir Alexeev, who's at the University of Alaska Fairbanks, and NSF for funding the RU program this summer. So a brief overview of what I'm going to talk about. So I'm going to talk about what energy balance climate models are, some of the feedback mechanisms that I'm looking at in my research, some quantitative representations of those feedback mechanisms, some results so far, and further work to be done. So energy balance climate models contain relatively simplified processes. So when you hear about climate predictions in the news, that's mainly coming from things called general circulation models. And energy balance climate models are a little bit different. They're not really used for prediction because they're not as accurate, but they take a lot less time and computational power to run. And they're a lot easier to understand what's going on in the model, whereas a general circulation model is really a black box model, so we don't know what's going on that's causing the results that we see. So I'm using energy balance models this summer, and I'm looking at two different feedbacks. So the first one is the ice albedo feedback, and basically the way that works is we start with warming temperatures here, and that causes ice to melt, which decreases the total ice area on the planet. That causes something called surface albedo to decrease. And that's basically just telling you how reflective Earth's surface is. And so when surface albedo decreases, less radiation is reflected back off the Earth, so more is absorbed. And so that causes the temperature at the surface to warm even more. And so you can see how that's going to build on itself over time. I'm also looking at the water vapor feedback, where again we're going to start with warming temperatures. That's going to cause increased evaporation. That a warmer atmosphere can also hold more of the water vapor that's evaporating. And since water vapor acts as a greenhouse gas, that's going to trap more heat at the surface and cause the temperature to warm even more. So again, we have this building cyclic process. So that's kind of a conceptual understanding of how these things work, but to really understand what effects these have, we need to quantitatively describe them. So the standard method for that is standard feedback analysis, and we're going to make a comparison to a reference system and compare that to a system where we have that feedback turned on. So you can see we're going to input a radiation that's going to cause an output that's either radiation or temperature, and part of that output gets fed back through the process, whether that's water vapor or ice albedo or something else. And that's going to cause an additional temperature change here. And so we can quantify that by either looking at a feedback parameter, which is basically just telling you how much more is being fed back by your feedback, or a gain parameter, which is really just related to the feedback parameter, but has this useful property, which says that the temperature change alpha, which is when the feedback is active, is proportional by that gain parameter to the temperature change when the feedback is turned off, so just the reference system. So this is a standard way of doing it. It's been done a lot, but the limitations of this are that you can either look at this on a global scale, so what is the global temperature doing, or you can look at it in a specific region of the world, but you can't get a sense of the non-local feedbacks in general. So a new idea was proposed by Dr. Alexeev and Dr. Jackson, and I've been investigating that this summer, and so it's a matrix-based feedback analysis. And so you can see that the inputs, instead of being just a single value, are now vectors, and we're also getting an output vector of the temperature. So that's giving us input radiations into a number of different regions, and then that temperature responses in each of those regions simultaneously. And again, some of the output gets fed back in through our feedback loop. You'll see that these equations over here are very much analogous to the original equations, and so again we have this relation between the temperature vectors, but if you're going to have that proportionality between vectors, you have to have a matrix instead of just a constant parameter. And so you'll also notice this new equation for the gain matrix that is related to sensitivity, and that sensitivity is coming from up here, and it just tells you if you input some amount of radiation, how much does the temperature change in a given system. And so those are things that we can actually get from our models, and so that's how we're going to calculate the gain matrix, and then from there the feedback matrix. So the model that I've been using is called the GREB model. So that's Globally Resolved Energy Balance Model. So as I mentioned before, it's an energy balance model that has 48 different regions of latitude and 96 different regions of longitude. So that's a large number of boxes. And it has a number of different processes active. So we have solar radiation coming in. We have thermal radiation coming up from the surface and out into space. We have a full hydrological cycle active. We have sensible heat advection and diffusion, which are all moving heat and water vapor around in the atmosphere. We have an active ice line, so the ice is responding to the temperature of the Earth. And we have deep ocean heat exchange with the surface. And so we use this model, which was developed by Dominguez and Floater, for some other things, and we modified it a little bit so that we could use it to do the feedback analysis we wanted to do with it. So this is showing you a temperature response to radiative forcing. So basically what's going on here is we're putting 1 watt per square meter of radiation, so basically increasing the sunlight that's coming in or causing heating, at a given latitude slice, and then looking at how much the temperature changes across the globe due to that forcing. And so we get these out for different models, and so we can fix the ice albedo feedback, so basically turn off the ice albedo or turn off the water vapor, and then compare the temperature responses when that's turned off and turned on. And from that, we're going to get the matrices required to calculate our gain and feedback matrix. So here are a few results. So for the ice albedo feedback, we have this matrix over here. So this is the feedback matrix, but it looks very similar to the gain matrix, actually, because there's a good approximation we can make there. So this is the feedback matrix, and you can see that, so this up here is the South Pole, and as we go over and down, this is the North Pole over here. And so you can see this feedback is fairly strong, and these values are basically just telling you how strong the feedback is in a region. So it's very strong here at the South Pole and at the North Pole, which is what we'd expect because that's where there's ice. At the equator, there's really not much going on. And over here, we have diagonal entries in blue and the sum of all the off-diagonal entries in orange. And so we can see that the off-diagonal entries have the same magnitude as the on-diagonal, which tells us that all those non-local feedbacks are really contributing pretty strongly to the feedback process response. So this is telling us more than just looking at the local effects would be, because if we were only looking at the local stuff, we would only see this blue curve and we wouldn't see as much of that orange curve distinctly. So this approach is really giving us new information about how these feedback processes are working. We also have results for water vapor feedback. So you'll see this is much more uniform across from the South Pole to the North Pole. And again, there's some pretty significant off-diagonal entries. And in fact, here again, we have the diagonal in blue and the off-diagonal in orange. And so you'll see that the sum of the off-diagonal entries is actually much larger than the on-diagonal. So these non-local effects are really strong. And it's important to be able to quantify those and look at them in addition to just looking at local feedback effects. So we've also made some comparisons to the standard feedback factors that you would get normally. So for example, so we can basically average everything out from our model and get the overall global parameter. And so for water vapor, we get something on the order of 0.36, and the standard literature value for that is 0.3. For ice albedo, it's on the order of, I believe it's 0.8, and we're getting right around 0.8 as well. We also wanted to test something called additivity. So in general, in the standard approach, feedback factors add. So water vapor plus ice albedo, the feedback parameters for those two should be equal to the feedback parameter for both of those feedbacks over both of those feedbacks being turned off. And so we tested that for our matrices, and you can see that the feedback sum, so that's adding the two feedback matrices together, and then the system where we have both of those active over both of those turned off, it is shown in solid and dashed lines, and it's very hard to see the two different ones, which shows us that we have really good overlap between those two sets, and so we're carrying over that additivity into our matrix approach from the standard. So some further work to be done. We want to better understand the physical consequences of this feedback approach because we don't totally know what exactly do these non-local values mean in terms of physical processes. And we want to develop a better explanation for the feedback matrix. The gain matrix, we know that it's just a proportionality between temperature responses. For the feedback matrix, we don't have quite as good of an explanation for that. We'd also like to analyze some other feedback processes in the GREB model. There are other things that we could turn off and on and see what effect that has and quantify those feedbacks. And also applying this approach to different models to check that it's still valid. These are my sources, and I'll take any questions.
10 minutes to the microstudy. Any questions? Whoever, yeah.
Additivity on water vapor feedback.
Yeah.
What's going on in the top left of the
Yeah. So that's because the atmosphere at the poles is drier than the rest of the globe, so there's just not as much water vapor there to have the feedback be having an impact. Yeah.
Can you go back to where you first introduced the matrix model? You were talking about how it improves on the previous model. I know it was before this. Yeah, there it is. So what actually is the matrix in this case? Like, what are the rows and columns?
Yeah, so I'm going to actually change the slide to this. So we're getting the columns of the sensitivity matrix directly by averaging out over longitude, because basically by forcing in each of these different latitude slices, that's like applying a base vector, so zeros in every latitude except for 1. It's like applying that forcing. So then we'd read out directly in the temperature responses the columns of the sensitivity matrix, and then those sensitivity matrices come in here. So we get the sensitivity when the feedback is turned on, multiplied by the inverse of the sensitivity when that's turned off, and then that gives you your gain matrix.
So then was it pretty computationally intensive to run the model?
Yeah, so the model takes about a second per year to run, and we want to run 50 years, 48 times, twice to get all of the data that we need for a single gain matrix. Yeah.
Did you write the code, and
Yeah.
did you write it here, or where did you?
So the GREB model is already, the code was already written, and so all those equations for the climate processes were already written in, and so that model was already written, but then we had to modify it to be able to add the forcings that we wanted and to be able to turn the feedbacks on and off. So I modified a code that was already written.
And the minutes that you quoted, were they on a local machine, or?
Yeah, so it's just a standard desktop computer.
Any other questions?
I guess I have one more. Yeah. In this video you showed us,
Yeah.
I mean, is there an implicit assumption here that, about why the lines sort of go up like this? Because you could imagine increasing the temperature in different ways rather than just sort of, scanning across. So
Yeah.
for example, increasing the temperature, over the landmass in South America might have a different result than increasing it over the sort of ocean part. And I was just curious about why this is the right thing to study.
Yeah, absolutely. So we're doing our gain matrices over varying latitudes. So when I show those gain matrices, each of the columns corresponds to different latitudes. And so we want to scan over latitudes for radiation so that we can get those gain matrices that tell you how how strong the feedback is at different latitudes. We've actually done it running over different longitudes as well. And so that gives different results, obviously, and we can see some interesting things from that as well. And we're actually in the process of running some data where it's just individual boxes. But this is just because, especially ice albedo is very latitude dependent, depending on whether there's ice or not. So that's why we chose to go over different latitudes. Yeah.
Great questions again. Any others? Okay, let's thank Mathilde again.